Today we're going to be talking about medians, altitudes, and perpendicular bisectors in triangles. So the definition of a median is a segment in a triangle from the vertex to the midpoint of the opposite side. Vertex to midpoint. From vertex to midpoint. And from our vertex to the midpoint. So each one of these is the midpoint. And the point where these medians meet is called a centroid. This is going to be important to us in later chapters. The centroid is always going to be inside our triangle. An altitude. An altitude is a perpendicular segment from the vertex perpendicular to the opposite side. So from a vertex, perpendicular. From a vertex, perpendicular. From a vertex, perpendicular. In a right triangle, the legs are going to be the altitudes. And then you're going to have one other segment that's the altitude. And then sometimes if you have an obtuse triangle, your altitude is going to be outside. So it's technically perpendicular segment from the vertex to the line that contains the opposite side. So there's my perpendicular. There's my altitude for that one. Now from this vertex, that one's a little bit more complicated. You need to extend this third side so that we are perpendicular there. And the point where the lines containing the altitudes meet is called the orthocenter. Again, that's going to be important to us in later chapters. And the orthocenter, if I extend, so that's the line containing the altitudes. So I'm going to extend all my altitudes so that they look like they're going to meet at a point. They're going to meet at that point right there, and that orthocenter is sometimes inside our triangle. In the obtuse case, it's outside. In our acute case, look, it was right there, it was inside. In our right triangle case, our orthocenter was right there. Okay, perpendicular bisector. It's a segment that is perpendicular to a segment at its midpoint. And the perpendicular bisector, that's the definition. It kind of tells us exactly what's happening. It's perpendicular, so I have a right angle to the segment at its midpoint. So that is congruent to that. And the point in a triangle where all the perpendicular bisectors meet is called the circumcenter. That's, again, also going to be important to us. And the circumcenter is going to sometimes be inside. Our triangle. In the case, again, of an obtuse triangle, I'll draw an obtuse triangle here. Let me try and draw in all our perpendicular bisectors. So I'm perpendicular at its midpoint. So first find the midpoint. Draw your perpendicular. Find the midpoint. Draw your perpendicular. Find the midpoint. Draw your perpendicular. In that case, right there, that point, I'll highlight it in green for you guys, that point is outside our triangle. Okay, if a point lies on the perpendicular bisector, the point is equidistant from the endpoints of the segment. If a point is equidistant from the endpoints of the segment, then the point lies on the perpendicular bisector. And equidistant means equally distant from the 2 points. So going back to the last picture, what that means. Okay, so if I have a point on my perpendicular bisector, okay, so I have a point on my perpendicular bisector. If I draw the distance from that point to the two endpoints, this segment's equal to that segment. Same thing if I have a point down here. The point down here. From the endpoints of this segment, that distance is all the same. Okay, so that's what that means. Distance from a point to a line is the perpendicular segment. So, distance from a point to a line is the perpendicular segment that's the shortest distance. Okay, that's going to be important to us when we start talking about something here in a minute. Okay, so now dealing with what we've been talking about. If AB is equal to BC, then something is the median of triangle APC. PB, because PB goes from a vertex to the midpoint of the opposite side. So that's PB. Okay, next. If PC is the perpendicular bisector of BC of something, then BC is going to equal DC. So PC is the perpendicular bisector of a segment. That's the segment that gets cut in half. So that's going to be BD. Okay. If angle APD is a right angle, so I'm going to draw in my right angle symbol. So I have a right angle in there. Then, what two segments are the altitudes? Well, the altitudes are going to be the segments that are the legs. So PA and PD. If PC is the altitude, or if PC is the median of triangle PBD, so this is equal to this, BC is equal to CD. Oh, then that's what I was looking for. I was looking for what's congruent. Then BC is equal to CD. Because PC went from the vertex of our triangle that we were talking about to the midpoint of the opposite side. Okay, next. If BC is equal to CD, and PC is perpendicular to BD, then PC is the perpendicular bisector of BD. Lastly, if PC was equal to, if PC is equal to AC, oh, I'm sorry, PC and AC are both altitudes of triangle PCA. So PC is an altitude, AC is an altitude. So those are altitudes. That's my right angle. So angle ACP is a right angle because the altitudes are going to intersect at a right angle. And those happen to be the legs of our triangle. Okay, now angle bisectors. So our angle bisectors. If a point is on the angle bisector of an angle, then it is equidistant. So if a point is on the angle bisector, so DA is the angle bisector, and point D is on the angle bisector, it's equidistant. So the distance from D to B is going to equal the distance from D to C, and I have to have a right angle in there. So that it's equidistant from the two sides of the angle. So if I have angle BAD equal to the measure of CAD, then DB is going to be equal to CD. Now, if a point is in the interior of an angle and it is equidistant, so from point D, when I calculate that distance, the perpendicular distance from the sides of the angle. Then it lies on the angle bisector. So now it's the converse of that. So BD is equal to DC. Then I have an angle bisector, so then that angle is equal to that angle. And the point where the angle bisectors meet of a triangle is called the incenter. And the incenter is always going to be inside our triangle. Okay, now dealing with our angle bisector. If BX bisects angle ABC, so BX is the angle bisector of angle ABC. So notice how I'm highlighting things. Don't be scared to highlight your angles. So then what two angles are equal? Angle ABX is congruent to CBX. And DX, now X is a point on my angle bisector. So the perpendicular segment to the edge of the angle, XD, is going to be equal to the perpendicular segment from X to the side of the angle, which is XG. Okay, now I'm going to erase that. DX is the perpendicular bisector of EB. So XD or DX is the perpendicular bisector. So it hits at the midpoint. So D is the midpoint. So then ED is equal to DB. And XE. So X is a point on our perpendicular bisector. XD is the perpendicular bisector. X is a point on that. EB is the segment that it bisects, so therefore X is equidistant from the endpoints of that segment. That means that XE, this segment here, is equal to XB, because X goes from X to B, so that's XB. All right, next example. If XB is equal to XF, then what is the perpendicular bisector of BF? So this is the converse of what we just did. I have a point that is equidistant from the endpoints of a segment, so therefore XG is the perpendicular bisector of BF, and XBF, angle XBF, is going to be equal to XFB. Because what do I have there? I have an isosceles triangle. So by our isosceles triangle theorem, that's how we have our congruent angles. Okay, XD is equal to XG. This segment is equal to that segment, then something is the bisector of another angle. Okay, so both of those intersect at X. So where does those intersect at X? So those are both equidistant from the edges of angle X, of angle ABC. Those are both equidistant from the sides of angle ABC. So therefore, XB is going to be our angle bisector. So XB is the bisector of angle ABC. Because my perpendicular segment from X was equidistant from the two edges of our angle. Okay, last example, and this is a proof. Prove the medians drawn to the legs of an isosceles triangle are congruent. So I have a given, I'm going to have a prove, and I'm going to extend my page because we're going to need a lot of space for our proof. Okay, so I have an isosceles triangle. So when you're doing these proofs, you're going to give me a triangle. Let's call it triangle ABC. So triangle ABC, and then when it says isosceles, give me the two congruent sides with AB congruent to AC. And then, okay, median. So the medians are going to be drawn to the legs. The legs are the congruent pieces, so my median drawn, CX is a median. BY is going to be a median also. So BY is a median. CX is a median. And BY is a median. Okay, so prove that the medians drawn to the legs of the isosceles triangle are congruent. That's what I'm trying to prove. I'm trying to prove that CX is congruent to BY. Okay, first, let's start out with our given. I have AB is congruent to AC. That's the piece that tells me it's an isosceles triangle. And that CX and BY are medians. Okay, now remember where you're trying to go. You're trying to prove those red segments CX congruent to BY. Let me highlight a triangle for you guys. If I could prove triangle XBC congruent to triangle YCB, if I could prove those two bottom triangles congruent, I would have corresponding pieces. So triangle YCB. So that's where I'm going to try and get to. Okay, take something from the given. I'm going to take something from the first part of the given. From the first part of the given, I know AB is equal to AC by our isosceles triangle theorem. I know that AB angle ABC is going to be congruent to angle ACB. Base angles are equal. So in those triangles, I now have an angle congruent. I have the common side. Let's put that down right away. BC congruent to BC. And that is by reflexive. Okay, so I have this side congruent. I might draw my triangles over here just so that I know what I have. I have angle and side. I have this angle, this side. Now if I could get another side, if I could get BX equal to CY, that might help me out. Okay, so if I could get BX equal to CY, that's going to help me out. Let's take the second part of the given. Step 4. What was the definition of the median? Median went from vertex to midpoint of the opposite side. So X is the midpoint of AB, and Y is the midpoint of CA or AC, that's by our definition of a median. Now step 5. That tells me that BX is equal to half of AB and CY is equal to 1/2 of AC. And that is by our midpoint theorem. And so notice how I first had to say that they were midpoints because I didn't technically say that in our proof yet. And then I had to say by midpoint theorem that they were half the length. Step 6. So step 6 then, I need to somehow get these segments equal. I know that AB is equal to AC. So from this step right here, AB is equal to AC from our first step. So therefore, if I multiply both sides by 1/2, I multiply both sides by 1/2, then our 7th step is going to be substitution. I can't substitute and say BX is equal to CY quite yet because I don't have an equation that I'm substituting into. So therefore, BX is equal to CY by substitution. So BX is equal to CY by substitution. So then I have my sides congruent. So now I can say that triangle XBC is congruent to triangle YCB, this time by side angle side. And then lastly, we can say that CX is congruent to BY by CPCTC. So that's a good proof, because remember, in this, the goal of the class is for you guys to for me to give you a sentence. You guys to pick out the given, the proof, draw me a picture, and write a 2-column proof. Okay, there are your lesson questions for the day. So please, for the triangle ABC, so your triangle is ACE. Your triangle is ACE. Name me the angle bisector, the median, the perpendicular bisector, and an altitude. And please make sure those are submitted on time.